here we go. Is it going? There we go. Okay. So as you all know, field testing is quite hard, especially to get actually significant results. And in particular, we have talked a lot about control and treatment experiments. That's a common practice for these control techniques. And that was also similar to what we were thinking of. This doesn't have to be exclusive to that, but it is a little bit more motivated by that scenario than some other types of experiment. And so when you're doing that, if you're looking for a small difference, it can be a bit difficult. And in particular, because when you have a control and treatment, the uncertainty of the difference usually, not necessarily, but is usually larger than the uncertainty of an individual measurement. It can kind of depend on if you have correlated uncertainties or not. But there is the advantage, though, that you can oftentimes assume that any uncertainties from biases are the same between the control and treatment, and then they just subtract and are negligible. So you're just left worrying about uncertainties from random errors. So just to drive that point home, I'm sure this is all familiar to most of you guys. So on the left here, this could be power or whatever quantity, but you're looking for the difference. And so you propagate those uncertainties. This is assuming they're uncorrelated in this case. Just for the sake of simplicity, let's say that they're about the same between the control and treatment. In this case, then, the uncertainty of your difference is 40% larger than the individual uncertainty. So just kind of trying to lay out exactly what that additional burden is when you're trying to find the uncertainty of a difference. And then to be clear, when we put this in terms of error bars, as we like to do, what you're looking for is an error bar where the 0 is not inside that interval. And then you could say that's significant. And then you can also do this backwards, which is all this showing. So if you have an expected difference, you could solve for making these same assumptions, solve for the uncertainty, individual uncertainty that you would have to achieve in your experiment if you're trying to work to drive down any sources of error and uncertainty. And so for that 4%, again, just arbitrary number, you have to get about 2.7%, which can be pretty difficult even in a lab to achieve. So this is what we want to answer. 2 questions closely related. So what's the minimum measurement duration? And that's the time just spent measuring. What's the minimum measurement duration to achieve a sufficiently small uncertainty in the difference between control and treatment to yield statistically significant and converged result? And notice there are words in here that need more definition. So, the user gets to define what significant and converged mean for them. And then perhaps more importantly for many cases is what we're calling the experiment duration. So what experiment duration is required to achieve the minimum measurement duration? And this gets into a subtlety of usually field experiments, could be any experiment really though, that you're not necessarily measuring all the time. And this is mostly important in this field experiment setting and for wind energy because you don't control the wind. So if you are trying to get certain conditions or fill a bin based on some sort of whatever binning you've established, you might have to wait a while to get that next measurement. And so that can add a lot of time to the experiment duration to achieve the minimum measurement duration that you need. And that was kind of our question was, for this experiment that we were imagining, we kind of wanted to have some sense of, okay, well, maybe we'll just get it at a few wind speeds, and how long would that take? Or could we do the whole power curve and things like that? So I'll go through this kind of high level quickly, and then I'll try, just for the sake of time, and then try to get into the case study where I think some of this will be a little clearer than at the high level here. But this is the method overall, and as I said from the beginning, I think it's really fairly obvious, though there are a lot of sort of subtleties and details to pay attention to. I realized as I started doing it. So you need to know when your experiment is, and you need to have some way of simulating the experiment, essentially. You have to have some information about the inflow, which you may have to do some QA/QC, things like this. But the big part is down here. You're going to use all this information to create inflows, run them in a simulation, and then that you're basically doing the virtual experiment. You're going to take the outputs, this data, and bin and process it with like a running uncertainty analysis, essentially, such that you can find the times at which you actually achieved what you wanted to in terms of significance and convergence. So much of this is flexible to different fields, different types of experiments at the high level, but I'll talk about it kind of specifically in terms of wind energy and then the case study. So what's a suitable simulation code, right? So most of this is pretty obvious that it needs to actually be able to simulate the things that you're interested in, and you have to within your expertise and judgment, know that it's accurate enough. So don't, choose a BEM code for something where you think 3D effects are important. You would need hopefully a validated turbine model that would help you ensure that you're not introducing additional errors in these simulations. And if particular aspects of the inflow are important to what you're interested in, then you need to make sure that those are also being simulated pretty well. But you can keep in mind that the statistical variance, and so by that I mean that when you eventually will bin everything, that if you represent the right amount of variance there, that might be sufficient, even if when you dive into like the time series results, you're maybe not seeing everything that you would expect to see. That's kind of a subtlety. I don't know. Okay. So to do these simulations, you'll need some way of representing the inflow. Ideally, I think the best case scenario would be that you have some Met Tower data, some historical data, and then you can literally just use that data to inform your inflows. But I think that you could absolutely do this based on sort of probabilistic data. If maybe you've seen a site characterization, you don't have the data, but you have the characterization that says, that these conditions happen with these probabilities. A little easier probably if they're in terms of like a temporal distribution, so that it's in terms of the time of year, day, that sort of thing. And that just is for that last step where we have to take this and translate it back into time. So yeah, we'll be binning it, but you do want to think about that again in terms of just what your experiment is and what you're interested in, right? Longer bins, shorter bins, they might add or miss things depending on what you're interested in trying to see there. And then, an acknowledgement that this is a simulation and numerical methods, especially this is sort of low fidelity, I would call it. They oftentimes are underrepresenting sort of that true variability. This is a whole area of research on its own. So just something to keep in mind. Maybe another reason why this is probably just getting at a minimum time. All right, this step's pretty straightforward. So when you have all that data, you'll process it into these 10-minute statistics, and then each inflow is used for a 10-minute simulation, and then each 10-minute simulation stands in for that 10 minutes of field experiment. And then for the processing, so you're going to want to, well, the normal thing to do is to bin on conditions, like wind speed and wind direction, things like this. And then in a given bin, you'll compute this running bootstrap. So as each sample is added to the bin, you update the bootstrap calculation again, and do this for all of the quantities of interest that you care about. And this is how you'll eventually be able to quantify that uncertainty. And then for convergence, it's a similar thing, but it's a running mean. And then you have some standard for convergence that you'll apply, and that'll tell you if you've achieved it. And so couple notes on bootstrapping. I feel like every time I go looking for more information about it, I learn new things. And so there's really not a firm agreement in literature from what I could find on the minimum number of samples, sort of a little bit on judgment based on how much variance there is in the data, but 8 to 25 was what I found. Was kind of the range. So that's could translate basically into how many samples you'll need in a given bin, depending on how you bin it, to make sure that you can do a robust bootstrap analysis. And then suggestions for around 15,000 replicates, so the number of resamples with replacement that you do. If you're not familiar, the main advantage bootstrap that I always think of is that it's not making an assumption about the distribution shape. So we frequently, or not we, but people oftentimes use standard deviation for a kind of measure of uncertainty, but that would assume a Gaussian distribution, and this does not. And then just a reminder that this 95% confidence interval that we all love to use is completely arbitrary. And even the guy who came up with it never thought that it would become a standard. So, all right, so let me go a little slower on the case study, because I think this will draw out a lot of these points. So we imagine this is all made up and all virtual, just for the sake of this demonstration. So we imagine an experiment at Sandia's scaled wind farm test facility, and that was pretty much because we had data there to use. So the site looks like this, where here's going to be turbine B with Met B and turbine A with Met A, both the Met towers upstream in this dominant wind direction here. So what we did to get a sense of control and treatment, to have a control and treatment, but also to parameterize the results by the size of the expected difference, was we just did tip extension. So we did a very straightforward, assumption that the power was proportional to the area, did the math to find the tip extensions that we would need for different expected power gains. And without any real design work, just linearly extrapolated the baseline tip in the OpenPass files to make those tip extensions. Very simple. And it, yeah. So then to make the inflows, we had the MET data, as I mentioned. TurbSim needs hub height, wind speed, turbulence intensity, and a shear exponent as the inputs for every single inflow. In addition to the Met Tower data, we also have about 1.5 years of another taller tower near the site that was used years ago to characterize the site. Or sorry, we don't have not the data, but we have the results of the characterization from that. So here's where we start to get into some of the details that become important. So the two Met towers, Met A and B, were filtered for working hours. So this, again, is representing what an experiment would look like at the Swift site, where we have only attended operation. So we can only do the experiment during working hours. And so over those expected months, 3 months that we imagine. But we took data from multiple years of the Met Tower. So those same months, but over multiple years. And that gives us kind of a more typical view of what those months look like, rather than 1 year where it was maybe a little bit different or something. Instead of trying to do like a more involved QA/QC of the time series of all the Met data, after binning the data, we looked at the statistics of each bin and then just used our site characterization to create thresholds. So if a particular bin had a TI that was higher than what the site characterization said the TI ever was, we just threw it out as probably erroneous. And similar for the other quantities. Just even though it would be odd if at 10 minutes there was correlated data, we did check that it was uncorrelated. As I mentioned, certain experiments you might want to do shorter bins, and so then it would become more important to make sure that you're not essentially repeating the same conditions, that these bins at this stage stay independent. And so for the experiment that we wanted to represent, we needed a total of about 2,500 10-minute bins from each Met tower. And it turned out that we had a lot of data in Met A. And so we just randomly selected from those to downsample to that number. And it turned out that we did not have enough data in Met B. And so here we had to randomly upsample. And this obviously could create an issue where we are introducing a bias depending on, if our sampling of conditions in Met B was sort of even or not. So we had to kind of accept that. I'll show, I think it's the next slide, how we can get a look at that too. But for the purpose of the demonstration, that's what we had to do. And so again, each of these becomes a TurbSim inflow, which is then one simulation and then 10 minutes of field data, essentially. Yeah, so this is what I was just talking about. So just another kind of important thing to maybe have a look at when you're doing this is to look at what the data is telling you as you make these bins. And so what we see here are the plots for Met A and B for each month, and then by day and by hour. The black line is representing kind of where we would expect to be if we had enough data. So you can see in the hours, we never have enough data to get to where we'd expect to be, but it is uniformly sampled. So that's maybe the more important part. It's fairly even across here. It's not like the Met towers worked well in the morning, but went down in the afternoons all the time or something like that. In the days, it's a little bit different. The reason we crossed the black line is because it's based on the experiment duration, but we took data from multiple years of the Met data. So sometimes a day might have lots of samples from multiple years, but then we'll never have a certain day. And here again, we can make some arguments if we had to say that these day-to-day variations maybe aren't as important as sort of the more larger seasonal ones. But also, this is just a demonstration of the method, so it's not critical. But this would be, for a real experiment, something important to look at. All right, so this slide, try to kind of remember the overall look of these three pictures here, because this will come up a few times. So this is showing on the left and right all of the inflows, the statistics essentially for all the inflows for Met A and Met B. Where we have the wind speed, the turbulence intensity, and then the color of the dot is the shear exponent. And so you see, it looks like there are more samples in Met A, and that's because, remember, Met B, some of these are used more than once because we had to upsample, in a sense. And then the other things to pick out from this are that kind of, this is, I think, fairly typical for most sites, that generally speaking, these low wind speeds have this higher variability, a larger range of turbulence intensities and shear exponents. And then as you get into the higher wind speeds, it kind of flattens out into a smaller range, less variability. You can see that in both Met towers, as you would expect. So we can make predictions from this stage, at least qualitatively, about what we expect in our results when we follow through with the rest of it. And so because of that high variability at these low wind speeds, you would think that there's going to be higher uncertainty. So I should just preface here, to keep things simple, I only binned by wind speed with my results. This would change depending on how you bin it. If you binned also, say, by turbulence intensity, you'd get different results, and I'll touch upon that later. But just binning by wind speed, you would expect then that this variability in the low wind speeds would create a greater uncertainty and slower convergence. And you can also see that there are fewer samples in these high wind speeds. We don't get high wind speeds as often, and so that means that they might not ever converge, and also we might just not have enough data in some of those bins for the bootstrap analysis. And then getting to the middle plot here, this is just showing the histogram after binning of how much data is in each wind speed bin for the two Met towers, where A1, if I didn't say yet, is going to be used for the baseline, and B1, the red, is going to be used for all of the tip extensions. It's kind of as if pretending that we could do all of the tip extension experiments at the same time. And so the only thing really to note here is just that there's a mismatch, right? So we don't have the same amount of data in each wind speed bin, and so we're going to have to be careful of that when we get into the sort of finer details of processing the data. All right, so here's a high-level look at results for 4 quantities of interest, and then 2 to kind of look at the controls. So the black X's are our baseline, and then the tip extensions are all of the dots. And as you can see, the tip extensions, they kind of stack up on each other with a bit of a pattern, and that's because they all have the same set of inflows. Whereas the black X is the baseline, has its own set of inflows, and that's why you see some points that stand out from the rest. So a few things just to note at a high level. When you look at it this way, before you bin it, these are all pretty smooth, right? There's no weird kinks in it. And so that will be important to remember as we look at what happens when you do bin it. And then I want to just point out some important wind speeds when we look at the controls. This was something I hadn't really thought about going into it, but it turned out to be really important to the results, and that's paying attention to where your controller is changing things. So you can see kind of, I don't know, high 6s, low 7s, somewhere in this area. We start to see that the pitch slowly increases with a big change in the pitch control, kind of around 10, 11. And then similarly, the rotation rate has a big change in what it's doing around 8 meters per second. So those wind speeds, we should expect to see maybe some interesting results because the controller could introduce kind of a variance of its own in a sense. All right, so here is sort of 2 different ways of looking at a very similar thing. So the left, the relative standard deviation. I saw another name for this the other day, and I forgot what it was, but it's just the standard deviation divided by the mean. And this is for each bin and for each quantity of interest. And then the right side is the percent relative error. So we're looking at just so far the individual measurement uncertainty. So for each rotor, divided by its mean, ensemble mean in this case for the bin. And so they show similar things. So you can see for power and flap, for example, or sorry, power and edge, that variability in the low wind speed seems to have a bigger effect on those than it does for, say, thrust and the flap moment. On this side, you can't necessarily separate a high standard deviation from a low mean, but you can see kind of over here how that variability adds to an increase in uncertainty in the relative error here. So that does kind of trickle through that high variability at low wind speeds. The other thing we can see is, well, that we should take a little caution in are these spikes at the high end here. Some of these might be, I shouldn't say erroneous, but for this plot in particular, we've applied the bootstrapping, and some of these bins we haven't looked at yet. They might not have enough samples in them, so this bootstrapping might be kind of meaningless in a sense. So that's something we'll have to look at later, but it's possible that these results are just sort of, it's not a place where we can really do the analysis, I guess what I'm trying to say. But we do also see some bumps where we expect to have enough data. So say, for example, these ones, you can kind of see it a little bit on the left side too, maybe around 7, 8. And so that, I think, is that change in pitch. What I think has happened here is that by binning, we've sort of introduced a variance in a sense that there are some data in that bin that have that change in pitch and some that don't. And so that kind of mix of data on either side of that change in pitch control has made this bin, has increased the variance of the data in this bin in a sense. Whereas you didn't see that, in these results, they're all smooth across that transition. But when you bin, it kind of artificially adds that in a sense, is my understanding of that. All right, one wall of text here just to go through some subtleties. So for the last of the calculations here, and I didn't go into this before, but so as I mentioned before, the number of samples in a bin between the controls and treatment, or control and treatments, is not the same. That was clear. So we have to address that. So for the difference in a quantity of interest, we start just by subtracting between the two. So we have the running mean of the control and the running mean of the treatment, and we subtract them. But eventually one of those is going to run out in a given bin. And so at that point, we just hold that ensemble mean and continue the subtraction with the other one that still has data left in its bin. And do the same thing for the running uncertainty. And here is where we also have to apply the standard that I talked about for having enough samples for the bootstrap. And so what we decided to do, because the data is a little bit bimodal in that those low wind speeds had really high variability and the high wind speeds had a lot lower variability, we're requiring the 25 samples, more samples for the low wind speeds, and only 8 samples for the high wind speeds. So dividing right at 8 meters per second. And so you go through this, and then you simply mark, this is the sample at which my significant criteria was met. And then for convergence, kind of similar, right? So a couple other details though. So technically, the reason you need this convergence standard is that you could have a significant result after one sample, in theory. So you also want to kind of make sure that you've achieved that converged result. And we do this with the running mean on the difference for a converged difference. We chose the standard of 2% of the ensemble mean, so it had to get there and then stay there, and also made sure that this was true for at least 2 samples in a row. And it couldn't include the last one because by definition, you get to 0 on the last one. And so again, you find where this criteria is met, and you just mark that sample. And then at the end, we'll translate those back into time. You pick the bigger of the two of them, right? So you've got 2 criteria now, one for significance, one for convergence. So to make sure that they're both met, you have to go with the longer one. All right. This is really fast, I'm sorry. So here's just looking at the uncertainty of the difference for power, just to give you some visuals here. So you can see how as you add samples, these error bars are shrinking. You can see maybe some important points here, like it's maybe hard to see, but this blue one, the smallest rotor, it goes above and below 0. So it's important to note that you have to reach significance and then stay there. So you have to look at the entire bin to make sure that you've remained significant. And then as I mentioned, some of these, like, okay, here's one with 7 samples. This one we're not going to be able to use because we needed a minimum of 8 samples. So here's a whole bin that when we apply that last criteria of minimum number of samples, we'll just have to throw this out. So we can't say anything here. And then similarly, the look at convergence. So this is the fraction that it's converged to the ensemble average. The main thing I think that is interesting here is that they're not all maybe what you think of with convergence, where it's a nice, slow asymptotic approach to converge. Because we're doing this sort of in time sample order, sometimes you get a result that suddenly throws it off and it goes kind of up and you have to then go back down. So it's not necessarily a monotonic path to convergence when you take them in order this way. All right, but then these next 2 are maybe the big results here. So this is experiment hours to produce and maintain a significant and converged difference from the control just for power. So we have our wind speed bins down here. For each bin, we have the 5 treatment rotors because we want to know how long the experiment takes for these to be significant and converged, for the difference to be, excuse me. So first I'll start where the results maybe look like what you may be expecting, and that's maybe so these middle bins here where we see clearly that the smaller rotors, the shorter tips, take longer, and that's because they're producing smaller differences. So we would kind of have this expectation that the smaller the difference, the more time it might take to meet these criteria for significance and convergence. And so that's what we see, that the stack of bars is going down to the right as you go to the bigger rotors. And these letters at the top are marking which of the two criteria determined the time. So the C for convergence and S for significance. You see mostly for this particular experiment, at least, it was actually the convergence criteria that was kind of stricter in a sense. And you can see clearly down here where there are a lot where there was not enough data. So these either never converged or were never significant. So you see a lot of rotors missing. We see some missing here too, and I suspect that's because of the high variability in these lowest wind speed bins. And then we see some weird ones where it's not in the order you expect. So kind of here where they go out of order, or where just one of them randomly sticks up. And it's a little bit hard to tease out exactly what is going on there, but they do tend to coincide in those wind speed bins where I mentioned that the controls were playing an additional role here. So these ones are around 8, these ones are around 10, 11. And so these were places where we saw that the controls were kicking in and changing the operation of the turbine. And so I think that's tied to why some of these rotors kind of, we're not seeing the pattern that we necessarily expect in these ones. All right, so then the next one is the measurement duration. So this is, so this one was how long you have to do the experiment for, right? So remember that the experiment is set up where we're not measuring all the time, just working hours. So this is, going up to 2 hours or 2,000 hours here. So that's, 40 hours a week for a year, basically. But that's because I think it's like 80% of the week you're not actually measuring. You're missing a ton of data. But if you just ran the experiment and you just want to know how much measurement hours you would need, it's a lot less, right? Fewer than 50 for all of these. And then this much better follows the pattern that we expect of sort of that the smallest rotors require a little bit more time than the bigger rotors. We see that we still struggle to have enough data at the high wind speeds. And we see that the high variability at the low wind speeds also makes it difficult for these ones to be significant and converge down here. And then this largely follows the histogram shape of our wind speeds. And that's because whereas this plot matters both how variable the data are, and it also matters when the data happen. So like in time order when they happen. This one, it matters how variable they are, but it only matters that it happened. We don't care about when these measurements occurred, just that they happen. And so we're just counting them that way. And so that's why it largely follows. It's a balance now between these wind speeds had the most data, but they still had a good bit of variability. And so they need a little bit more time. These wind speeds had less data, but a lot of variability. So some of them don't even pass the criteria. These wind speeds had low variability, but not a lot of data. So some of them don't pass the criteria at all here. And so it's kind of a balance of those two things. All right, so let me wrap up, try to quickly get through the rest of this, just a couple more. I want to just point out briefly, there's a whole other way you could think about this. So frequently when we have a project, the constraint really is budget or time, or sort of the same thing. So you could imagine instead that, okay, well, I can afford this much experiment. This is how long I can measure for. What standards can I achieve? And so you could instead run this through. This is just looking at power for one of the rotors. And now looking at it broken down by different confidence intervals and convergence levels. So getting stricter as we go from the top left to the bottom right. And it's kind of hard to see because we're talking, maybe a difference of an hour or two on a scale of 2,000 hours. So you can't always see that it's getting a little bit more difficult as you get to stricter requirements, and it's less difficult for these ones. So just picking out one of those in particular, it's clearer here to see how this changes as you go to stricter requirements for confidence interval and convergence level. And the reason these jumps are not in 1 hour increments is because this is the time you spend waiting to get that particular condition to fill that bin. So to go from this 95% confidence interval from 4 to 3% convergence level, you're waiting this many more hours just to get the condition that you need to fill this particular bin. And I want to go back 1 second because I forgot something that was really important. A colleague pointed this out to me, and unfortunately, it's too late to get this in the paper. It would have been really cool to explore this further. This could be another paper. But he pointed out that if we bin by more than one variable, so if we, let me take this down here. So that we said that these have high variability. There's a large range of TI in these lowest wind speeds. If we had binned by wind speed and TI, it's possible that not only would more of these rotors pass the criteria for significance and convergence, but they would have done it in less time, right? Because we're essentially removing that variability by bidding by TI at the same time. And so similarly, while this makes it look like, okay, I'm going to need a long measurement time for some of these, you can play with this, right? You can bin by different things and see where the optimal is to reduce that measurement time by binning out that variability. The consequence, of course, is that you also have less data in your bins now. So there's a trade-off, but you can find where you get that sweet spot and find the least experiment and or measurement time in doing this. Okay, so I've reached the conclusions. I'll just leave these up and say thank you. I think I about hit my time, Eric, hopefully. Happy to take questions. There is a preprint that you can, of course, go look at. Hopefully the final is approved pretty soon and all the revisions will be up too. Thanks, everyone.
Well, thanks, Dan. That was super interesting. Yeah. Start with some questions. Soren, I think you had your hand raised first.
Yeah, thanks, Dan, for a very nice presentation, very thorough and in much detail. We tried to do something similar using LES. Of course, there we don't have the same amount of samples. But when we try to do that, then one of the things we started looking into is what is the impact of the 10-minute duration of the statistics, because that's sort of underlying in your analysis. Can you maybe comment on that?
Yeah, so it wasn't something I played with. The farthest I got was just to do due diligence, and I made sure that since I had time series that I could look at, I could confirm that 10 minutes didn't run any risk of my inflow bins being correlated with each other. For us, it was the correlations time were kind of 2 to 3 minutes, so we could have gone down to 5 minutes even, and that was something I considered when I found out that I didn't have enough independent samples for one of the Met towers. I thought, okay, well, I could do shorter bins. But I think the main thing, just kind of in theory, that I would be concerned about is you'd have to just match it to your quantity of interest. So if you think your quantity of interest is highly dependent on really short time scale phenomena, those will sort of get averaged out if your bin is too long. And kind of on the other side, if you think that it's a long time scale phenomena, then you might want a long time scale bin that sort of matches that. And that way, my thought there is that way that phenomena stays in the right bin in a sense. So you're still going to be pulling averages from it, but at least I don't know if I said that right. But that phenomena kind of tracks with the right bin rather than getting sort of split across two bins that then maybe have different statistics in them. Does that make sense? So I haven't tried anything, but just thought about it.
Yeah, no worries. It's interesting because I would expect that if you averaged over longer, then maybe you would need less samples, but maybe it would turn out to be the same amount of time in the end, right? So when you talk about 2,000 hours that you need to experiment, but again, I haven't tested it. We've just looked at it in LES where we have significantly shorter time series.
Yeah, it'd be really interesting to try it. There's so many little knobs to tweak when you think about this, and I know I couldn't do them all, but yeah, I'd be really curious to see which ones matter most. That could be a follow-up paper of its own, probably.
Cool. Mike, you had a question?
Yeah, just want to echo. Yeah, really, really nice presentation. So thanks for that. So yeah, my question was actually related to the one raised by your colleague. So
yeah,
do you think you could use this method to actually identify what are the primary determinants that dictate the statistics in a given bin? So you also mentioned the pitch example, right? So it sounds to me like that kind of result should suggest that pitch or some aspect of the controller should also itself be incorporated into the bin knowledge. So maybe this method can be actually used to identify what should be the definition of the bins.
Yeah, that was one of the points I definitely wanted to make here, was that this allows for that I guess experimentation before the experiment, in a sense. So you can, since you've done the experiment virtually, albeit lower fidelity and sort of all sorts of caveats potentially, but you can I think at this point I can only really imagine sort of a trial and error process. But yeah, for example, say that pitch bin. Maybe that one bin should have been 1 meter per second wide about that change in pitch, so that you kind of smooth out the variability that's introduced there. As my colleague pointed out, there's potentially a favorable payoff to binning on more than one parameter if it means decreasing the variability. And you don't have to do that across the board. You could just say bin by TI and wind speed in those lower wind speed bins. And leave the higher wind speed ones just bin by wind speed, because there you have fewer samples, and so maybe you don't want to split it up into more bins. You could try all of these things and try to find the optimal, and go into your experiment a little bit more informed on sort of how long you should measure, and in particular which conditions are maybe most critical for you to capture in that experiment. And the other thing I don't think I mentioned, but we've talked about switching schedules. That's another thing that you could do in this, right? So simulate the control method for the whole time, and the baseline method for the whole time, and then go through and sort of artificially pretend that you're taking data from one or the other at different times, and see how that influences your results as well.
All right, Nathan?
Yeah, really nice set of work here. Maybe I just missed this, but how were you using the two different? You took data from two different Met towers and binned it independently, and I didn't quite follow how that then was used in determining the results later.
Yeah, so we imagined a side-by-side simultaneous control and treatment, and that's actually what the Swift site's set up for. That's why it has the two turbines facing the dominant wind direction with the Met tower aligned with them. So one Met tower and one turbine was just the baseline, and then the other Met tower and turbine was all of the treatments. And because this was virtual, we just imagined we did them all at once, right? So that way we could parameterize by the difference. So they had different inflows. They're probably they're very similar, right? Because they're taken somewhat simultaneously, but yeah, technically different. Yeah, and we assume the turbines are identical.
Yeah, it makes sense. I guess in a lot of the somewhat similar idea work that I've done, I've sort of taken side-by-side turbines and assumed that the inflow is the same at any given point in time, which obviously is an incorrect assumption, but.
Right, and I think to get a
Yeah.
sense of it, you could do that, especially if they're not too far separated. It's probably not a terrible assumption, but since we had the data, we did it this way. Yeah,
Makes sense. Thanks.
Right. Yeah, one question I have. So you showed the minimum measurement duration to achieve significance and convergence for each wind speed bin, and so the greatest number of samples was around 5 or 6 meters per second, and then it's lower at very low wind speeds. And so some of those you just don't have enough data to achieve convergence or significance. But for those that you do you know why those require less data than higher wind speeds? Because I would expect that the variability in the wind to just keep increasing as wind speed decreases.
Yeah, so you're talking about these ones here.
Yeah.
So that's a good question. I see it as kind of a balance of number of samples and variability. So these ones here have a lot of samples and kind of a middle variability, which seems to be the case that makes it take the longest. Whereas these ones So some of these are missing, right? Some rotors did not meet criteria. So there's so much variability that these smaller differences didn't work out. But the other ones, there's a lot of data. So despite the high variability, I think that they, with the lot of data and the big differences, maybe it's an interplay of the variability and the fact that they're bigger differences. Maybe those don't sort of translate through. The variability doesn't translate through as much for the larger rotors and those large differences. It's difficult to tease it out without really trying to look into every bin and those details. So I'm kind of, this is my best interpretation so far. Yeah.
Mm-hmm. Okay. Yeah. So it's maybe the minimum number of measurement hours. It's not really. It doesn't just depend on the variability of the wind at those low wind speeds, but also the number of samples you're collecting, and that can, when you do the bootstrap sampling, that can affect what the variability in your bootstrap statistics are.
Right. Yeah.
Cool. All right. Any more questions for Dan? All right. Well, thanks a lot
Thanks,
again
everybody.
for your presentation.